Imagine if every time you tried to remember a conversation you had yesterday, you actually had to pause your brain, walk over to a filing cabinet, open a drawer, and read a transcript just to formulate a reply.
That sounds exhausting, but yeah, that is exactly how every modern AI agent works today.
Right. But a new paper we are covering today on AI paper slop titled Metis, Memory Foundation Model. This is from Ziyu Zhang and a really stacked team of researchers at Memtensor, Renmin University of China, NUS, SJTU, and Tongji University. It's trying to give AI a native brain.
And the core takeaway for anyone building agents right now is that we might actually be moving past retrieval augmented generation, or RA, entirely.
Yeah, moving past it completely, because Metis is the first prototype of a true memory foundation model. So instead of bolting on an external vector database, it internalizes memory directly into the model's parameter.
Right. We are talking about dynamically compressing, storing, and updating historical information entirely during a standard forward pass.
Which is huge. It creates these native memory states that are end-to-end trainable, completely parallelized, and, it just skips the latency of querying an external database altogether.
It is a fundamental shift in how we think about agent architecture. Because, for the last couple of years, if you wanted an LLM to retain state across a session, you basically had to build scaffolding around it.
A lot of scaffolding.
Right. You engineered an external module to fetch text chunks. But Metis brings that entire storage and retrieval process inside the neural network itself.
And if you're looking at the current industry standard, mostly RAG, like we said, that external scaffolding is a massive bottleneck.
Oh, absolutely.
The paper points out 3 really glaring limitations with external memory that, honestly, anyone who has deployed an agent in production has definitely felt. And the first one they label as decoupling.
Yeah, decoupling. You see that play out immediately in a standard RAG pipeline. You have a retrieval system, which is usually an embedding model hitting a vector database, and you have your generation model, the LLM.
Right.
And they just do not share the same optimization target. The retriever is, it's just optimizing for semantic similarity. It finds text that looks like the prompt and stucks it into the context window.
But semantic similarity doesn't necessarily give the backbone model the optimal representation it needs for actual reasoning. It's just passively receiving this raw concatenated text block.
Exactly. The LLM didn't choose how to organize or represent that memory. It's forced to just condition its generation on whatever the retriever decided was relevant.
Which leads directly to the second problem, which is blocked gradients.
Right, because retrieval from an external database is a discrete mathematical operation. You are fetching hard chunks of text. You cannot easily backpropagate gradients end-to-end through, like, a text query.
Because the computational graph literally breaks at the database layer.
Shatters, yeah.
You can't pass a continuous gradient through a discrete SQL or vector search. So if you're an ML engineer trying to fine-tune an RAG agent for a highly specific, legal or medical task, that gradient block is a nightmare.
It means your LLM can get better at reading the retrieved documents. But the mechanism for finding and storing those documents remains stubborn. You're fighting the architecture.
And people try to patch this, right? We see teams using reinforcement learning, trying to optimize the retrieval process by feeding reward signals back based on the final output.
They do, but that is wildly inefficient and unstable. It basically prevents you from doing any domain-specific post-training on the memory mechanism itself.
Because the model's reasoning weights and its memory fetching mechanism are essentially walled off from each other during optimization.
Precisely. And then there's the third limitation, which is sequential latency.
Oh, the killer for production systems.
The absolute killer. A user prompt comes in, and the system halts. It queries the vector database, waits for the fetch, re-ranks the context, appends it to the prompt, and only then does the LLM actually run its forward pass.
It forces a sequential bottleneck on the entire system.
Yeah, the actual reasoning process is constantly interrupted by file retrieval.
I always think of standard ARG like a junior developer who hasn't learned the syntax of a new language yet.
Oh, that's a good way to put it.
Right. Like they write 3 lines of code, pause their workflow, minimize their IDE, open Stack Overflow, read the documentation, and go back to the IDE. It's external, sequential, and slow.
Very slow.
But Metis, theoretically, is the senior engineer who has internalized the syntax. They just write the code directly from memory without breaking flow.
But to actually upgrade this model from that junior developer to a senior engineer, you have to rewire its brain.
You have to physically change the standard transformer to internalize that memory.
Exactly.
So let's talk about how they alter a standard causal language model to do that. The researchers split this into two concepts, the native memory state and the native memory procedure.
Right, so the native memory state refers to the persistent, dynamically evolving parameters inside the backbone. It is the physical storage, basically a matrix of weights that holds the historical information.
Got it. And the procedure.
The native memory procedure is the computational mechanism. It's the actual forward pass operations that autonomously write to and read from that physical storage.
Okay, so to pull this off, they replace standard transformer blocks with what they call the Metis block. And this introduces two entirely new components. There's the hypermemory block for storage and the local memory block for utilization.
Let's start with storage.
Yeah, because if you're taking in a constant stream of conversational context, how does the hypermemory block save it without just infinitely inflating the KV cache?
Well, the hypermemory block acts as a compressor. At a given step, it takes the intermediate hidden states from the previous layer, but it does not store all of them.
So it's throwing things away.
Yes, it compresses them into a fixed-size, dense memory network. So first, it pre-normalizes those hidden states. Then, it scores each token using a learnable importance vector.
So it's judging the tokens.
Exactly. It calculates an importance distribution, evaluating which tokens actually contain valuable semantic payload. And finally, it selects the top tokens based on that score and dynamically aggregates them into the compressed matrix.
Wait, hold on. If it's doing a hard top K selection to pick which tokens to keep, that is a discrete, non-differentiable operation.
It is.
We literally just criticized ARG for having blocked gradients because of discrete text fetching. How on earth are they passing gradients through a top K cutoff to make the hypermemory block end-to-end trainable?
The researchers anticipated that exact mathematical trap. If you just apply a hard top K cutoff, your gradients die immediately.
Right.
So to bypass this, the paper implements something called a straight-through estimator.
Oh, interesting. I've seen that technique used in quantization, but how are they applying it here?
The trick of the straight-through estimator is that during the forward pass, the model pretends it made a hard, discrete choice.
It fakes it.
Yeah, it grabs only the top K tokens, which gives you the computational speed and memory efficiency you want on the way forward. But during backpropagation, the algorithm basically substitutes the continuous probability gradient for the discrete one.
So it essentially tricks the math.
Completely.
It tells the backpropagation, hey, don't worry about the hard cutoff I made earlier. Just route the gradients through the continuous probability distribution of all those important scores I calculated.
That's it, exactly. The gradient bypasses the discrete cutoff step entirely and flows freely through the continuous probability distribution that scored the tokens in the first place.
That is so clever.
Right. Because of this mathematical sleight of hand, the scoring mechanism becomes entirely end-to-end trainable. The model learns, via gradient descent, exactly how to score what is important over time.
Okay, so we get the discrete efficiency on the way forward and the continuous learning on the way back. That covers the hyperblock doing the compressing and storing.
Yeah.
But if the hyperblock's entire job is to compress and store the data, there has to be a retrieval mechanism on the other side. Like, how does the model actually search its own latent space when it needs that info?
That is where the local memory block comes in during inference. It takes the current input prompt and computes a memory query using an optimizable projection matrix.
Okay.
And then it uses this query to perform memory attention over the compressed memory state we just built.
Oh, I see. So it acts like a targeted searchlight, sweeping across its own internalized parameters rather than sweeping across a vector database.
Exactly. And once it extracts that relevant historical information, it has to merge it with the present.
Right, it needs to synthesize it.
So it combines this memory readout with the standard attention branch using a learnable balance parameter, which they denote as gamma.
Gamma?
Yeah, and gamma weighs how much the model should rely on the current input context versus the historical memory state.
That makes perfect sense. So if the user's prompt is completely self-contained, like, I don't know, what is 2 + 2, gamma leans entirely toward the standard attention branch.
Right, it doesn't need to check its memory for that.
But if the prompt says, compare this to the revenue figures you mentioned 10 turns ago, gamma dynamically shifts the weight, pulling heavily from the memory attention branch.
Yes, and the critical difference from RAG here is that this memory attention runs in parallel with standard attention.
Directly inside the native layers.
Yes, there's no sequential pausing. It's all happening at once.
Okay, so the Metis blocks provide the physical architecture, but bolting a new transmission onto an engine doesn't mean the car knows how to drive itself.
No, it definitely doesn't.
You can't just take this architecture, throw it into standard pre-training on raw web text, and expect it to magically understand complex state management.
You really can't. Standard next token prediction won't teach lifecycle memory management.
Right, so how do you explicitly teach the weights to update a specific fact, or even harder, forget something?
To solve this, the researchers developed a mid-training pipeline. They constructed a massive, highly specific data set derived from 27 different public benchmarks.
Oh, 27.
Yeah, and this data set was engineered to force the model to practice 4 core memory operations. Remember, reflect, update, and forget.
Okay, the first two seem relatively standard for language models. I mean, remember is just stating a fact in the context and querying it later, forcing the model to pull from the memory state.
Right.
And reflect is multi-hop reasoning, introducing isolated facts over time and making the model synthesize them.
Exactly.
But update and forget, this is where neural networks traditionally fall apart.
Oh, neural networks notoriously struggle with isolated unlearning.
Right, because in a vector database, updating or forgetting is trivial. You just find the row with the old fact and you delete it, or you append a new row that supersedes it.
It's a simple CRUD operation.
Exactly. But how does an LLM explicitly overwrite a fact dynamically during a forward pass without causing, catastrophic forgetting in its static weights?
Well, we have to delineate between the model's static weights, the general knowledge it learned during pre-training, and this new dynamically evolving memory parameter matrix.
Okay, so they are separate.
Yes. When we talk about update, we are presenting a modification to a previously stated fact. The model isn't rewriting its foundational knowledge.
Oh, I see.
Instead, it's learning to adjust the representation within that specific dynamic matrix, so the new fact supersedes the old one in the latent space.
Okay, so if you tell the model, actually, the meeting isn't at 3 p.m., ignore that. How does it physically manipulate a matrix to erase information? Does it learn to generate some sort of destructive interference?
You are hitting on the exact mechanics.
Wait, really?
Yes. In a continuous latent space, forgetting often looks like generating anti-vectors.
Anti-vectors, that sounds like sci-fi.
It kind of does.
Yeah.
But mathematically, the model learns to adjust the dynamic weights by introducing negative gradients or conflicting semantic directions that effectively cancel out the previously stored fact.
So it suppresses that specific activation so the model won't hallucinate it later?
Precisely.
But how do you train that mathematically? I mean, what does a loss function for forgetting even look like?
That was a huge hurdle, and the researchers solved this with what they call a reconstruction objective.
Reconstruction objective? How does that work?
During this mid-training phase, they don't just ask the model to answer questions based on the memory. They force the model to explicitly regenerate the stored reference passages word for word later in the sequence.
Wait, so they feed a passage in, let the hyperblock compress it into the memory state, clear the context window, and then say, spit that exact passage back out.
Yes.
That is brutal.
It is, but if the model perfectly reproduces the stored reference, it proves the dynamic memory state successfully retained the source with minimal loss.
Right.
By tying the training to this reconstruction loss, the model gets immediate, mathematically precise feedback.
So if the data set tells the model to forget a revoked fact, and the model fails to generate that destructive interference, the revoked fact will literally bleed into the regeneration.
Exactly. And the reconstruction loss will then heavily penalize the model, forcing the dynamic parameters to become incredibly precise at state management.
That's brilliant, because the native memory procedure is fully differentiable thanks to that straight-through estimator we unpacked earlier. The gradients from that reconstruction loss flow all the way back into the hypermemory block.
Right. It physically adjusts the importance score, teaching it exactly what semantic patterns to keep, what to overwrite, and what to drop.
Okay, the architecture is brilliant. The mid-training pipeline forces the required behavior. But for the ML engineers and DevOps teams listening, theoretical elegance doesn't pay the cloud computing bills.
No, it definitely doesn't.
The immediate suspicion here is deployment overhead. If you're storing unique memory states inside the model parameters for every active user session, doesn't that just entirely blow up the VRAM requirements?
It is the make-or-break question for real-world adoption. If native memory requires 10 times the GPU VRAM of a standard model, nobody is going to deploy it at scale.
Exactly.
But the paper addresses this efficiency directly. First, as we established, the memory utilization runs in parallel. so you save on latency.
Right, no waiting around.
But the real engineering win, the mechanism that keeps the VRAM footprint viable, is their use of low-rank decomposition.
Singular value decomposition, or SVD, the ultimate cheat code for machine learning efficiency.
SVD is crucial here. So in a standard setup, the full rank memory state in Metis has a rank of 1024.
That is a massive matrix to keep pinned in VRAM for every single user session.
It's unworkable at scale. So the researchers ran an ablation study where they applied SVD to these persistent memory states, basically decomposing them into much smaller matrices to see how much they could compress the memory before the agent started failing the memory benchmarks.
Let's think about why this works conceptually for a second. SVD basically finds the most important underlying patterns in a matrix and discards the noise. And conversational memory is probably incredibly low rank by nature. I mean, human dialogue and contextual facts have a lot of inherent predictability and low entropy.
They really do.
Like, you don't need 124 distinct mathematical dimensions to represent the fact that a user's favorite color is blue.
That is the exact underlying mathematical reality. The semantic information required for memory operations is highly concentrated.
So what were the results?
The metrics they discovered validate this perfectly. They found they could compress that rank 124 memory state down to a rank of just 16.
Wait, 16? Down from 1024?
Yes, and they still recovered full rank performance on the MEMUPS benchmark.
Oh, that is insane. To visualize this, it's like taking a gigabyte-sized, incredibly verbose server log file and zipping it into a 10-megabyte archive.
I love that analogy.
You just keep that tiny zip file in your active storage. And then when the model needs the context for a new prompt, it essentially unzips those 16 dominant semantic directions right inside the attention layer.
Yep.
You save massive amounts of memory overhead while maintaining the full fidelity of the original logs.
And keep in mind, MEMOPS is their rigorous gold standard benchmark for lifecycle memory operations.
Right.
So at rank 16, the model is still executing complex updates and unlearning flawlessly.
Which proves that deploying Metis at scale is actually feasible.
Very feasible.
You aren't provisioning a dedicated H100 GPU just to hold one user's long-term memory state.
No, you're not.
You get all the benefits of native memory, the end-to-end optimization, the parallel processing, the lack of external database latency without paying an impossible VRAM tax.
It really is a best of both worlds scenario.
Metis looks like a massive leap forward for agentic architecture. But, you know, we do not deal in hype on AI paper slop.
We certainly don't.
Every prototype has trade-offs, and the paper is actually very transparent about where this model currently struggles. And the biggest limitation they self-report is degradation on very long-term tasks.
Yeah, that's an important caveat. The hypermemory block compresses information into fixed size parameters. If you have a short or medium length interaction, the compression is virtually lossless.
Because it's not overwhelmed.
Exactly.
Yeah.
But if you try to compress a massive novel length amount of information into that same fixed size matrix, the resolution inevitably degrades. The algorithm is good, but you just can't defeat information theory.
Right. If you try to zip too many files into that tiny archive, eventually the files get corrupted.
Yeah.
And that leads directly to their second limitation, which they call information confusion.
Oh, this one is fascinating because everything is being blended into a dense, continuous latent space. The semantics can sometimes bleed into each other.
I always picture this like mixing different colors of paint in the same bucket.
That's a great visual.
Because a discrete vector database is like keeping all the paint colors in separate jars, right? They never touch, they never mix.
Right.
But in a continuous latent space, if you tell the model three highly related facts, the representation boundaries can blur.
They definitely do.
When it tries to pull that memory later, it might confuse the details, mixing up the subject of one fact with the object of another.
The muddy paint analogy is perfect. It is the classic trade-off of neural networks.
Yeah.
You trade the discrete certainty of a database row for the continuous differentiable power of a latent space. But still, for a first prototype of a memory foundation model, this architecture is a stunning piece of engineering.
It really is. And the best part for the researchers and engineers listening, the code and the model weights are completely open sourced.
That's huge.
You can pull them right now from GitHub and Hugging Face, test these memory blocks yourself, and see if you can break them.
I highly recommend people do. The shift from external to internal memory feels reminiscent of when natural language processing moved from explicit rule-based syntax trees to deep learning.
Oh, wow. That's a big comparison.
I think it's warranted. Bringing the functionality inside the differentiable computational graph just opens up entirely new optimization pathways that we are really just beginning to explore.
Which leaves us with a pretty wild industry implication to ponder for a second.
Okay, let's hear it.
If memory foundation models like Metis solve the long-term context problem natively, and we no longer need to retrieve text chunks from an external database to give an agent a brain, what does the future look like for the multi-billion-dollar vector database industry?
Oh, that is the question, isn't it?
If the large language model is the database, are vector DBs just a temporary bridge technology? Just something to think about while you're compiling your next project. We'll see you next time on AI Paper Slop.